This is the second lecture of chapter 2 about properties of fluids. So the chapter topics are as follows. We were done with the introduction and density and specific gravity in the first lecture. We talked about different types of properties, intensive, extensive, specific. We talked about density, specific gravity, and also the equation of state and the ideal gas law. The topic of this lecture is vapor pressure and cavitation. I will also show you a video about energy and specific heats, compressibility and speed of sound, surface tension and capillary effect. So these three topics here, this one, that one, and this one, you don't have to read the book. And all what you have to do is to watch 3 videos which are just 1 minute each. So as usual, I'm going to show you one video and then I will keep the rest for you. Viscosity will be a main topic that will span for many lectures. So again, this is my main topic here, which is vapor pressure and cavitation that I will discuss in this lecture. So vapor pressure and cavitation is my main topic. I will show you a small clip about or video about energy and specific heats, and I will keep these two topics for you to watch. So let us start. I would like to start with this question, which is, what is the boiling temperature of water? What is the boiling temperature of water? So take a few seconds, think about it. Very simple one. Okay, so if someone asks you this question, you have to tell him your question is wrong. If someone asks you what is the boiling temperature of water, then you have to tell him at what pressure. So he has to specify, or she has to specify, the pressure at which he is looking for the boiling temperature of water at. So if I ask you the question now, what is the boiling temperature of water at 1 atmosphere, then you can tell me, for example, 100 degrees centigrade. So this leads us to many questions then. What do we mean by saturation pressure? What do we mean by saturation temperature? What do we mean by vapor pressure? And what do we mean by partial pressure? So take a few seconds, think about those questions. Okay, so let's see and answer those questions. So the first thing that you have to understand is temperature and pressure are dependent properties for pure substances during phase change. What do you mean by this? Suppose you have water, and this water is in a pan, okay, and the combine, and you are heating this water. And this water is at atmospheric pressure. P is equal to 1 atmosphere, which is this. So I can heat the water, and then you can find the water at 20 degrees centigrade. I can heat it to 30 degrees centigrade, 40 degrees centigrade, etc. 50 degrees centigrade, and I can have water at 1 atmosphere, 20 degrees centigrade till all the temperatures you want. So here at 1 atmosphere, I can have water, liquid water, at different temperatures. So the temperature and the pressure, they are not dependent, they are independent. However, when I reach the 100 degrees centigrade, when the temperature here reaches 100 degrees centigrade, then I will have phase change. The water will turn into, or the liquid water will turn into, water vapor. So at 1 atmosphere and 100 degrees centigrade, water will be converted into water vapor. Liquid water will be converted into water vapor. So they are dependent. Temperature and pressure are dependent. When are they dependent? When we have phase change. Okay, so temperature and pressure are dependent properties for pure substances during phase change processes. This is what I'm saying. So at the phase change, they are dependent. For example, the water will boil at 20 degrees centigrade and 2.34 kilopascal. The water will boil or will change phase at 250 degrees centigrade and 3973 kilopascal. Those are dependent. However, as I have just told you, at 1 atmosphere, for example, I mean here, at 1 atmosphere, you can find all of those temperatures of water, so they are not dependent. I hope this is clear. I hope the statement is clear for you now. Now, at a given temperature, the pressure at which pure substance changes phase is called saturation pressure. So if I specify for example, the temperature to be 100 degrees centigrade. So this is my given temperature. Then the pressure at which a pure substance changes phase is called the saturation pressure Psat. So at this temperature, the saturation pressure of, or whatever, 1 atmosphere is called Psat. At a given pressure, so suppose now I'm talking about the other side. So suppose I'm talking about at 1 atmosphere, okay? The temperature at which the pure substance changes phase is called the saturation temperature. So the saturation temperature of water, let us say, at 1 atmosphere is 100 degrees. The saturation pressure of water at 100 degrees centigrade is 1 atmosphere. I am sure you have taken this in thermodynamics. Now, this is another concept which is very important for me, which is called the vapor pressure. The vapor pressure. So the vapor pressure of a pure substance is defined as the pressure exerted by its vapor in phase equilibrium with its liquid at a given temperature. What is the meaning of that? So suppose I have a container and I just put some water there. And let us say that the temperature is 40 degrees. I placed it in a room and this container is sealed. So after some time you will notice that there will be a little bit of water vapor here. And maybe you will notice that this level will just go a little bit down. Why is that? Because some of the water will be turned into vapor. Okay, and this vapor here will got some pressure. So if I'm going to measure let us say the vapor pressure here, if I measure the pressure of the molecules of water in the vapor phase, this will give me the vapor pressure. Why is that? Because the water vapor will got enough energy to leave the liquid phase into the vapor phase. There is an important thing to say here is that there will be a phase of equilibrium, okay? A phase of equilibrium. What do you mean by this? I mean, there will be reached a state where the water evaporation, the rate of evaporation, let us say the water that is leaving the liquid phase into the vapor phase is equal to the rate of water coming from the vapor phase to the liquid phase. So at this time, then I can, let us say this is the vapor pressure. So I have to wait till equilibrium is reached. Now, suppose the temperature of the water is raised into 50 degrees centigrade. I mean, the same experiment, the same thing. This was water. And now I have at 50 degrees centigrade, I kept the water there. The water was just evaporating from liquid to vapor and then from vapor to liquid. When I reached this stage or this equilibrium state, I came here and measured the vapor pressure. Do you think the vapor pressure here in case number 2 will be more or less than in case number 1? So case number 2 is at a higher temperature. So actually the vapor pressure in case number 2 will be more. So let us say this is P2 and this is P1. So P2 will be greater than P1. Why is that? Because the water molecules at 50 degrees centigrade will have more energy to leave the liquid phase and go to the vapor phase. So you can see from this simple illustration that as I increase the temperature, the vapor pressure of the substance will increase. Why? Because the molecules will have more energy to leave the liquid phase into the vapor phase. So let me repeat this for the last time. The vapor pressure of a pure substance is defined as the pressure exerted by its vapor in phase equilibrium. This is the, let us say this is the vapor, which is in phase equilibrium with the liquid, okay? At a given temperature. I have to specify the temperature. So I hope this concept is clear for you. Now, there is another thing which is called partial pressure, and partial pressure is defined as the pressure of a gas or vapor in a mixture with other gases. And also, you have studied this before. I'm not going to spend a lot of time on this concept because I'm not going to use it that much in this course. So, by now, I talked about saturation pressure, saturation temperature, vapor pressure, and partial pressure. Okay, I believe I answered this question already. What is the effect of temperature on the vapor pressure? So, you know the answer for that. I've just said it in the, previous slide. Now, this is the answer. As the vapor pressure increases, or vapor pressure increases with temperature. So, as temperature increases, vapor pressure increases, and I told you why. A substance at higher pressure boils at higher temperature. So as you can see, a substance at higher pressure. So if I have a substance at 1 atmosphere, which is 101.3 kilopascal, it will boil at 100 degrees centigrade. If I lower the pressure to 2.3.4 kilopascal, actually the substance will boil at 20 degrees centigrade. It will boil at room temperature if I reduce the pressure to 2.3 kilopascal. However, if I increase the pressure to around, let us say, 4000 kilopascal, then I need to raise the temperature to 250 degrees centigrade so let us say, the water will boil. So as I increase the pressure, then the water or the substance will need more temperature, more energy for it to boil and to change from the liquid phase to the vapor phase. And hopefully you know why now. Okay, so why I'm teaching you this vapor pressure business, which seems that is more related to thermodynamics. So there is a concept which is called a phenomenon which is called cavitation. And it is a phenomenon that we hate in the fluid mechanics. Actually, we don't want it to happen. So any idea what do we mean by cavitation? So let's see what do we mean by cavitation in the fluid mechanics and in the next slide. So the reason for the interest in vapor pressure is the possibility of the liquid pressure in liquid flow systems dropping below the vapor pressure at some locations and the resulting unplanned vaporization. So, actually, we are afraid that the liquid pressure in liquid flow system will drop below the vapor pressure and then my liquid will turn into vapor. And we don't want this to happen because usually our system is planned to deal with liquids, not vapors, and this will result in many problems for our equipment, for example, pumps, etc. For example, suppose we have water at 10 degrees centigrade, or suppose, for example, water at 10 degrees centigrade may vaporize and form bubbles at some locations, for example, at the tip of an ampulla, where the pressure drops below 1.23 kilopascal. So suppose I have a distribution system, suppose I have a pump like that, and water is flowing in the pipes through the pump, and then suppose my system is designed to handle, let us say, um, a certain temperature and pressure. But now if the water at 10 degrees centigrade, here as you can see, so water at 10 degrees centigrade, if I want to keep it as water, then I have to keep the pressure here. If the pressure dropped below 1.23, then the water will vaporize. Okay, the water will vaporize. So the water, now the liquid phase, will turn into vapor phase, and then I will have bubbles of water. And those bubbles will harm my instruments or my equipment. For example, the impler, which is the المروحة impler of the pump. So as long as then I am keeping enough pressure on the liquid, then it will not turn from the liquid to vapor phase. However, I have to make sure that, for example, in this case, suppose the temperature is 30, then at least I need to keep the pressure as high as 4.2 kilopascal. If the pressure dropped below 4.25, then I will start to have the cavitation. And we don't want cavitation to take place. So the vapor bubbles, called cavitation bubbles, since they form cavities. Okay, as you can see, they are like cavities in the water. And they collapse as they are swept away from the low pressure regions. So they will collapse. And once they collapse, لما ينفجرون هذه البubbles, they will generate high destructive, extremely high pressure waves. So once those bubbles collapse, they will generate extremely high pressure waves. And what is the effect of those high pressure waves? As you can see, this is an ampler. Okay, so erosion on the blades of the mixed flow pump, as you can see on the ampler. So once they break, once they collapse, they will start to cause erosion on the blades. So this phenomenon is called cavitation, and it is an important consideration in the design of hydraulic turbines and pumps. So cavitation must be avoided or minimized in most flow systems, since it reduces performance, generates annoying vibrations, كثير من الاهتزازات, noise, and causes damage to equipment. وممكن في النهاية إنها هي تسوي damage، ممكن هي تخرب الأجهزة اللي عندنا. So cavitation is not good for our equipment, and it happens as we said a minute ago. Okay, it happens here. The possibility of the liquid pressure. When the liquid flow system dropped below the vapor pressure, and there will be unplanned vaporization. So this is why it is called cavitation, because I will have cavities of vapor inside the liquid. And I told you why it is not a good thing for our equipment. So this is a quick example. I just covered it a minute ago. So in a water distribution system, the temperature of water is observed to be as high as 30 degrees centigrade. The temperature is observed to be as high as 30 degrees centigrade. Determine the minimum pressure allowed in the system to avoid cavitation. So I gave you this table here. So as you can see, I'm talking about 30 degrees centigrade. So how much do I have to keep my pressure so that I don't have vaporization? So I have to keep my pressure at least at 4 point, let us say 3 kilopascal. So as much as I keep this much pressure on the liquid, it will not convert into vapor. But if a pressure dropped below that, then I can have vaporization. Okay, I can have vaporization. And this is the answer. So in water distribution system, uh, the temperature, actually this is the same as the statement before. And the answer, as I just showed you, it is the minimum pressure, which is Psat at 30 degrees equal to 4.25 kilopascal. So I have to keep the pressure at least 4.25 kilopascal. So this ends this topic, which is the vapor pressure and cavitation. And you know what's the meaning of vapor pressure, and you know what is cavitation and why we are interested in this phenomenon. Now, the last thing I will talk about is I want to show you a movie which is a short one about energy and specific heats, and then I will keep these two topics for you to watch and comprehend as you have done before. So let me show you the movie now. The specific heat required to raise the temperature. So this is the definition of specific heat. It says the energy required to increase the temperature of substance by 1 degree. Different fluids have different heats. Different specific heats. And you know that different substances, different fluids, they have different specific heats. And also depends, the specific heat depends on the process. Into a fixed volume. The amount of heat at constant volume. I can have one type of specific heat, which is C sub V. Allow the gas to expand freely. And I can have another one, which is C sub V, C sub P. K equal to C sub P. And K is equal to the ratio of C sub P to C sub V. Is it important? Okay, so this is, for example, the short clip or the short movie about the specific heats. And there are again two more movies that I want you to watch, and this will be enough for the other two topics. Okay, so you don't have to go and read them from the book. And this ends this lecture.